Hi, everybody. So wanted to talk a little bit about history here and why we started working on Mongo in the first place, right? Because I think it's kind of interesting to go over. So I was at DoubleClick at the beginning and designed the original system there, and as you can imagine, that was non-trivial. Once you're serving 20 billion ads a day or 500,000 a second, it got to be a pretty big system. And of course, back then computers were much slower, right? Because this was in 95, 96. So, and there was a number of challenges we had. Part of it was just that there was no tooling for doing internet infrastructure yet. When we started, there was no such thing as a load balancer, and if you have one of those, it's very helpful. And this picture shows a Cisco local director, which I remember the first one of those we bought, and I looked at the back of it, and the serial number was 7, and I was like, oh, I wonder if this thing will work, but it did, so that was good. So there was a lot of things like that, which were there wasn't any sort of obvious way to do them or best practices yet. You just had to make it up as you went along. So some of these things are easier today, but some aren't. Scaling was hard because we didn't want to buy a mainframe, obviously, so we wanted to use lots of machines. So it was, how do you partition the problems up? We used Oracle for some data, like for business objects and things like that, but it was just too much data to use for everything, so we ended up writing our own key value store internally and building a bunch of other things too. We had one project where we manually did manual sharding with MySQL, and what I've just seen over the years is just over and over again sort of the same problem being solved. So we started thinking about can't we do something about this? Instead of doing it all from scratch. And there's been some solutions for a long time, like Google Bigtable, but they're not available, right? You can't use it. So we wanted to make something that everybody could use. So this has always been a need, but it's even more of a need now. So it's paradoxically, computers are faster now, but in a lot of ways, scaling is actually harder. Which is a little surprising, but let's look a little at why that is. So computers are still getting faster. Moore's law still works. But we're also trying to do exponentially more work, right? So we watch videos on our phones, and so as compute capacity or compute per dollar goes up, we seem very good at making use of it, right? So you're still going to have to work hard to do things with a reasonable amount of hardware because we're just going to do more, right? We're dealing with more data, we're doing more with it. So this is going. So it's sort of the question within me. Well, what's the problem? And this is the problem. Is that clock speeds aren't going up. So computers are still getting faster, but clock speeds aren't going up. So the way they're getting faster is they're adding more cores. So for the same price, you can get a computer with twice as many cores as you could a couple of years ago. So number of transistors still going up, but the clock speeds aren't. So it won't be long where it'll be a case I could say, well, I can't give you a CPU core that's fast at any price, but I can give you 1,000 cores very cheaply, right? So then it's a question of, well, what do you do with 1,000 cores when you want to solve one problem? So this notion of parallelism is going to have to be inherent in what we're doing. And some other trends drive this, right? And what we want to do here. Cloud has a lot of properties that go with horizontal scalability, including use of commodity hardware they're in, and the clock speed thing relates to a few things, but one is that the power usage would be completely unreasonable if you keep going up there. So this is sort of obvious perhaps, but you have a server and we want to scale it. We need more capacity. So the way we used to do it is you buy a bigger server. But nowadays, it was always expensive to buy a bigger server, non-linearly expensive. But nowadays, it's getting to be a case you just can't even buy a faster server beyond a certain point, and that delta between a entry-level server and the fastest one you can get is going down and down and down. So to some degree, you can still do it, although it might be expensive. But we'd much rather do this, right, where we can increase our cost close to linearly. But in a database, that can be hard, and you can just imagine if it gets a little bigger, how do all these machines coordinate to solve arbitrary database problems? And if you try to do this with a relational database and you do not make any special assumptions, it's very hard, right? If we make some assumptions like it's a star schema and we're going to bulk load all the data at night, then it starts to become very tractable. But if we don't, it's really hard or intractable. So, and this slide is just going back to this notion of parallelism. So we're going to need a tremendous amount of parallelism at all layers of the stack, not just the database. And some of these we already have it pretty well, right? The UI, so application servers, they're good at using a lot of computers, a lot of cores. So that's pretty good. Caching, that scales out really nicely. Memcached, and it's pretty easy to scale out. Network scales up nicely, right? A switch can handle kind of interchange of data from a lot of servers very well. So that sort of technology works pretty well. But there's a couple layers here where a lot of work needs to be done. Data processing, so Hadoop is a big step there, right? How do you do a lot of processing in a horizontally scalable way? If I don't give you Hadoop, it's going to be a lot of work to build something that does all that. So that's an example there of progress being made. And then the database layer might be the hardest thing here in this picture in terms of making it highly parallel. So we need it in all of them, but it's particularly difficult there. And so we were, a few years ago when we were starting the project and thinking about starting it, we felt like there was this need to scale horizontally, and we wanted such a system. And then it was a question, how do you do it? And so our point of view was, well, distributed joins is a hard problem. We're not smart enough to do that with full generality. So maybe we should do something differently. I remember back then we were thinking a lot about cloud computing, and that was part of the catalyst. That we were big believers in that trend. And this was approximately 4 years ago. So the one thing you have in the cloud is just this notion of horizontal scale is just intrinsic to it, right? So we could do that, say, in web app tier, but how do you do it with the database? And we started thinking about, well, should we take something like Postgres or MySQL and take the code and change it and add some things to it? And our conclusion was, it's not going to work. We're not going to be able to make that work. So in the end, we couldn't find anything that we really gave us those scaling properties in the way we wanted. So we decided to build something new. And we decided if we didn't do joins, that the problem would then become solvable. Of course, that creates a few issues. How do you do anything interesting then? So that was then the challenge then. And of course, if you're not doing joins, it has to be a non-relational data model, right? So then you would ask, well, what is the data model? So we had to choose a data model, and there's a lot of possibilities. Kind of like Bigtable has sort of a multi-dimensional table type data model, or Amazon Dynamo is kind of a pure key value store where the value could be anything, so the model therein didn't really matter, although it couldn't reach in and manipulate that stuff. So one of the things we wanted to do was to pick a data model that would let us write code quickly without a lot of friction, right? So we're changing the data model because we have to solve this problem, but can we also solve some other problems around software development. Mapping from objects to relational, as we know, is hard. Can we do some stuff around that and some other things to make programming easier? So there was then this philosophy with the project to make sure that was a high priority. So where we were coming from, and as we built MongoDB, is we want to solve the scaling problem, but not at the expense of developer productivity and making it easy to write code. So if we make it harder to write code, forget it. This is not a good idea. So that is absolutely central to the philosophy of MongoDB, and it has a lot of implications. Is it easy to write? Is it easy to write code? But is there enough functionality there that you don't have to do special things yourself to get you to everything you need for a use case, right? So if you take away, relational databases are very powerful, right? They have a ton of functionality, right? So if we drop 75% of that functionality and use something else and you go build an app, you can do it, but you're going to have to kind of reinvent a few of those things yourself. So the philosophy with MongoDB is keep as much as you can, right? There's a few things, if you keep them, you can't scale then, right? If you could, this problem would already be solved. There's lots of smart people who worked on relational databases, so you have to leave some things out, but don't leave out most things. Leave out as little as possible. So that was the idea and the philosophy. And what we left out was joins, and basically very complex transactions. So in MongoDB, you can do atomic operations on single documents. So you basically have ACID properties on a single document, but you don't have fully generalized transactions because distributed transactions are also very hard to do. I mean, not between 2 or 3 machines. You can just do 2-phase commit. But if I need to do them across a 1,000-node cluster and with lots of parallelism, it would be very hard. So this was kind of the philosophy and kind of where we started and how we were thinking about the problem. And another thing we were thinking about is, how we write code has changed. The sort of object relational thing is pretty obvious to us all if we're programmers at this point. But there's other things going on too. For example, we're doing agile development methodologies, right? So you're doing iterative development. I mean, it's super common now, and it works great compared to waterfall. But that doesn't really map very well to the way databases work, traditional databases, right? Because if I'm doing a release every day, I don't want to have a schema migration script per day, right? And I mean, not every day would you have to adjust the schema, but it would be a lot more often than you would have in the past. If you design the whole system up front, in theory, you got the schema right up front, where here we're going to be making continuous little incremental changes. So we kind of need something that's more compatible with that these days. So that's one thing. And another issue is there's a lot of programming languages today are dynamically typed. Maybe you can think of one. I think it's the subject of the conference. But and that can be very powerful. I think there's there are cases where I find statically typed language is really helpful for various reasons, but dynamic is also very helpful for different reasons. So it's interesting to think about that you can have the same thing in databases, right? So databases, relational database management systems are statically typed. And we don't usually think of typing in the database very much, but it's there. The schema is our declaration of type. So if you look at this update statement in SQL, actually I have a typo. I meant to have a number there for ABC. So update item set x equals 99. Well, we've defined it that x is one, that x is a column, and two, that it's a number. So, at the bottom there, I've shown like a, kind of a C structure, which would be strongly typed. This is kind of analogous to what we're doing in the database, right? So in our code, static typing is clear to us, but we get the same thing in the database. So it would also be nice if we're using a dynamically typed language to have a dynamically typed database, right? So that was part of the thinking too, and it's sort of just challenging kind of pre-existing assumptions and actually things that have made sense for a long time. Relational relational database concept is in my opinion, one of the most successful kind of technologies and ideas in computing, right? It's 40 years old and still used every day, right? And for a lot of stuff. So that's pretty amazing. We're not using any programming language that were created 40 years ago, right? And everything else in computing has changed a lot too. So that's pretty amazing, but it was 40 years ago, so maybe something else is appropriate in our toolbox in addition or instead. So that was kind of how we were looking at things. The catalyst was this need to scale, need for parallelism, and then the opportunity that came out of that was to make development easier, to take away some friction that as some of these new things we do as we write code have come into play. So, we had to pick a different data model. So, obviously there's a lot of options. So what we decided we liked is a document-oriented data model, and specifically a JSON-based data model. So documents are JSON. You stick them in collections. There's a dynamic schema in the sense that different documents in the same collection can have different fields or different types for different fields. So, JSON, we have a standard space. There's an RFC, language-independent way to store object style data. And so we like that, right? I mean, most or all of the programming languages we use today are object-oriented, so that's good. We'd like it not to be coupled to one language, right? We'd like to be able to go and look at the data in the database without reading the program. I mean, that's actually one of the big ideas in databases is to separate the data from the program, and enough that we can go look at the data without having to read the program. And so we want to maintain that. We want a format that's easy to read, right? I think for a technical person, JSON is pretty easy to read. And for example, XML, right, has a lot of the same aspects as this, but JSON's easier to read. So that's one thing we liked. Making something where it's easy to code and fast to code was an important part of philosophy. Another part of philosophy was sort of elegance, like from a developer perspective, right? So in my opinion, JSON is more elegant than XML, even if you were to tell me they were had similar capabilities. They are a little different, but just the general idea. I mean, the other good thing about JSON is you already know it. And then specifically, though, we did some tweaks, right? Is that we created this thing called BSON, stands for binary JSON, which is a binary representation of JSON. And we wanted to do that for a couple reasons. And it wasn't for compactness, right? I mean, JSON's actually pretty compact. If you think about x:3, the number 3 is only 1 byte long, right? In a typical program, it's probably 4 bytes long, right, or longer. So it wasn't about compactness. It was about two things. The first was fast scannability, right? Imagine I have a JSON document. It's 2 megabytes in size, and I want to look for a certain field. Well, if I start scanning through it, it's going to be expensive because if I'm just going kind of brute force through the whole 2 megabytes, and in addition, I'm going to have to do some things like count nesting of braces and brackets and quotation marks, and that's pretty awkward. So in BSON, there's a little bit of header information on objects, so you can skip over an object pretty easily. So fast scannability was something we needed to make the database reasonably fast. The other thing is we added a couple data types. We added a date data type and a byte array data type. So we felt like a database should have a date data type, so we added that. And if you need to store a binary byte array, there should be a way to do that. So you really never use base 64 in encoding in Mongo because of that. So, but the idea was to keep it as similar to JSON as possible. So there's a specification on bsonspec.org, and one thing we'd like to see is and we already see this some is for BSON to be used as widely as possible for non-MongoDB related things, right? So it's a serialization format, right? So you could use it to pass data around using a message bus or something like that. It would be very appropriate for something like that. I'd like to see other databases use it. I think that would be interesting. I mean, other databases already use JSON, so that's not a particularly big leap. So that's how we came to that. And one other note here is that it says object-style data, right? So if we go back a ways in time, there was, of course, object-oriented databases, and there was a couple issues with them. One was that most code then wasn't written in an object-oriented programming language, so that was a bit of a difficulty. Another one is this sort of, can you read the data without reading the code? Well, sort of, but a little harder. Our philosophy is don't store things about the program in database. So class hierarchies and linking between objects and methods, we don't want that to be in there. It should be something where, if you read and write it from one programming language and have another app that's reading and writing it from the other language, that should be equally easy everywhere with sort of no bias towards a particular one, except the bias towards objects, perhaps. Or, I could, in some ways, they're like C structs, right? Structures in C, not necessarily objects. You can nest, you can have arrays with them, in them. So they're probably more like C structures, but object-style data is pretty similar, right? So that was the idea there. So let's look at a specific example, and this is in the context of sort of agility or code faster, right? So let's say we're writing a content management system or a blogging system, right? So we're writing this app ourselves, and the idea here is you can post blog posts and people can go on the website and view them. So pretty straightforward. So we start out with this basic structure, which is, this is a blog post, right? It has a title, has an author, has text, the body of the item. So we get that working. Obviously that wouldn't take very long. And the site's up. And now we want to add some more functionality because we're doing this iteratively. So, let's say we want to add tagging, right? Which we would want to add. So we might do something like this. But the key thing to note here is that if there's already 1 million blog posts in the system, you don't have to go touch any of those existing ones. It's just when tags are added to an existing one, then the array will show up. And if you insert a new blog post that has tags, that's no problem either. So what happens if that field is missing is it just evaluates to null. So the database doesn't really mind if fields are missing, and it doesn't, if you try to query them, it doesn't error out, right? And it doesn't necessarily mind if they're different types either. So in this particular example, where, say, find me all the blog posts that are tagged with news. And, of course, this one is tagged with other tags, too. So that's kind of interesting because generally this syntax in Mongo, that's saying where tags equals whatever's on the right side. But if tags is an array, it actually says where this value is within the array is the interpretation of that statement. So that's nice. So one of the key things here is the system knows how to reach into these objects and understands their structure, right? So it's not a key value store, right? Key value store to me means sort of primary key to some value, and the value can be anything I want, and it's opaque from the point of view of the store. So here it can reach in and do a lot of traditional things for us. So we're doing an ad hoc query here, right? So that's kind of like I think in a traditional SQL system, you would do a join here, and you could easily do that query as an ad hoc query too. Now, one thing to note here is we don't have joins, right? So this would have been 2 tables if you normalized it. So what we've sort of got here is the data you could think of as being pre-joined. And then the database can still do the same operations a database with joins would have been able to do if the data is embedded, right? Sometimes it doesn't make sense. So for example, author Joe, if we had a bunch of information about Joe, it really wouldn't make much sense to put it in every blog post that Joe wrote, right? That would then be, what we call denormalization, right? But if Joe is the username of the author and is basically immutable, if we put it in every blog post by Joe, that is not denormalization, right? It's a foreign key then. But then in addition, you can imagine having an authors collection if we do want to get more information about Joe. Well, there are no joins, so you have to do that link traversal yourself. But you can, right? If you have this blog post, you can do a one-line query to go get the object for Joe. So there is a little bit of a trade-off there, right? But there wasn't a good alternative that we could, at least that we could figure out on how to then scale with no loss of generality. I mean, sometimes people ask me, it's like, well, why not have the database do that link traversal for me? And like in this case, it would be pretty easy, right? But it's a question of, well, does that generalize, or is it? And if it doesn't, how do you explain what it does and doesn't do? So it doesn't generalize. So we didn't want to do that. So we got our blog system up, we did our tagging, and now we're adding more functionality. We're adding voting, right? So here we have number of votes for this post, and we're also remembering who voted, because we don't want you to vote more than once. So that's the idea here. And one thing that's interesting here is that if we want to do this without a lot of work on our part as the developer, we need atomic operations. Right? We need some transaction capabilities. Not very complicated, but we need some. Because what we would like to do here is if we increment votes and add a new voter to the votes array, we would like that to be all or nothing, right? We'd like both of those to happen. And in fact, what we'd really like to do is we'd like to do a transaction that is, if Jane is not in the voters array, add Jane to the voters array and increment votes by 1. That's what we really want to do, right? We don't want 2 votes from Jane coming in concurrently from different client servers and then possibly both of them being applied and she gets to vote twice and she perhaps ends up in the array twice, right? So, and you can do that here. So it's not hard at all. So, but if we didn't have that, we could still find a solution, but now all of a sudden we're doing more work, right? So the idea here, or the philosophy here is do less work. And I may not achieve it all the time, but that's the philosophy. So now and we're working iteratively here, right? So next day we want to add comments, and we do this. So I mean, as you see, there's a lot of nesting here and embedding, but they're really not that different than what you might do in a program. So we can add this. But every day we're adding new stuff, and we're not having to go do anything fancy in a database to deal with the fact that there's new fields. The other thing that's important, though, going back to don't make things difficult, is it easy or hard to manipulate this thing, right? So let's say you want to find me all the blog posts where Gora commented, right? So if we don't have a good amount of query capabilities, then it's not going to be, we're going to have to do it ourselves rather than database. So, but here we can do it, comments.by is Gora. So what this will do, coming back to if it's an array, check for membership in an array, is this will say, find all the blog post where by equals Gora for some element in the comments array. So that's what it's doing, right? So that's nice. It's, the query is pretty compact, and we can do ad hoc queries. And then, but one thing that's very important is we can also create an index on that, right? So we can say index all the by values and stick them in the B tree, right? So in this particular document, if this index exists, it's going to add 3 keys to that index's B tree, right? So we're not adding 1 key to the B tree necessarily. I mean, if we would if it's a singleton value, but if it's an array, we'll add all the values to the B tree. and so that's very nice, but it's also, how that we get useful things done without having joins, right? You need that, right, for this sort of situation. And then we might compare to a relational implementation, right? So in relational, if we normalize this out, we might have 10 rows in 4 tables, right? And that's not too bad, right? But you can just imagine as you build bigger and bigger, more complex systems, as we all know, it gets to be a lot to manage. And even one simple thing, like say in relational here, we have this structure. If I just say, give me the post, right? Give me the post and everything in it. I mean, we can do that, but we might do multiple queries, right? So, or we could do something fancy to try to get it all at once. But I think you either do, the clean way to do it would be multiple queries to get one object, or we could do tricks and things to get it all at once. So, so it's just interesting to compare that. And once again, like we talked about before, it's like, can I manipulate this easily or not? Because if I can't, maybe I'll use it because I have to scale. But if I don't have to scale very far, I won't use it because it's harder, right? So don't be harder. So this is just an example of some of the things you can do. Sorting, operations like greater than or reaching into objects and indexing on all these relevant things. So that was important to us. So that is kind of the crux of what I want to talk about. We have more time, though, so we can do some questions if you want. Right, so what if Joe changes his name? So, yeah, that's a very good question. So you have a couple options then, right? So we could put an object ID for Joe in all this blog post, right? But then if we wanted to print out a blog post, we need to go get the actual name for Joe. So we'd have to do a query to go get that, which is what we call linking, right? So if we added the object IDs, then we stay normalized, if you will, or not denormalized, right? But if we have the string Joe in 100 blog posts, then Joe's name changes. We were denormalized. So sometimes you will denormalize like that because it just works out okay. And then I don't have to do the linking myself. But then a lot of times you will normalize by having a separate authors collection and keeping all the mutable data over there. Yeah, so that's a good example of where some of the pros and cons come in. I think another interesting example is if you think about an order, just a purchase order or something like that, right? So that's kind of a classic example in relational where you have order, an order line item. You probably also have a customers table and that sort of thing. So, if the line items of the order were within the order table, that wouldn't necessarily be denormalized because if there's no repetition of redundant data, right? Now, maybe, though, there's the name, the description of the SKU, though, is in each line item, right? So then that would be repetition. If we went to, if we wanted to change the name of the SKU, right, which would happen, and there's 1 million orders out there that would have a line item for that SKU, then that would be denormalization. But if we had just the SKU ID, quantity, and price, that to me that's not denormalized because there's no kind of redundancy to that in the system. Same thing with the customer information, right? So if we put the customer's name in every order, that's redundant and denormalized. But if we have a customer ID in there, it's not. And then the one interesting, though, aspect of that particular use case is you might want all that in the order anyway, right? Because if I have a historical order, I may want the old description in it, right? If I pull it up a month later and the description changed, I'm not sure that's the right thing. And the same thing with other things like the customer's address, right? The customer's address changed in the customer's table. We probably want the old customer address in the old order. So obviously there are many cases like the author name where it is totally valid, but that's one where might want it the other way anyway. And sometimes, though, you will denormalize just to make something easy. What else? Back there. Nope.
We have microphones out if you'd like to go to the mics to ask questions.
So, with DoubleClick, I think the initial title of this was House Serving All Your Ads. So, what in specific did Mongo do for you relating to ad serving?
Yeah, so the question was in the context of DoubleClick in that what did Mongo do for us, or what was the relevancy? So a few things. One, well, I think a key part of it was we needed something that could store a tremendous amount of information. So a good example is we wanted to be able to limit the number of times any one person, i.e. web browser, showed a particular ad, right? So we needed to keep, relatively simple tuple, which is kind of user ID, ad ID, number of views, right? So the only problem is there's trillions of those that need to be stored, right? So, and this was, back then, computers were 100 times slower, right? So that became a pretty significant scale problem. So we wrote something which was our own internal key value store. It was called UIS, User Info Server. And that was our solution to the problem. And it ran on many servers, and it addressed that need. But there was two problems with that. One is we had to write it from scratch, right? And the second problem was it was not flexible, right? We got it running and it worked great, but the structure of the information you could put in those records was fixed, and if we wanted to change it later, it was a pain. We had to go change the code, and of course we could have wrote it to be flexible, but it was more work, and so the more flexible version is Mongo. The other thing that was a problem with it was kind of scale out, right? If you want to, we can do partitioning manually ourselves. It's not that hard, but it gets to be a little harder later when you want to change things, right? So with that system, we just kind of hashed out the keys you wanted to look up on to the different servers in the cluster. But then later, when we wanted to add more servers, that was a pain, both because I want to take let's say I had 8 partitions. I want to add a 9th, right? So I really want to get of the things that are hashed over here, 1/9 of them over here, and keep all the other ones where they were. So that's a little tricky too. And then the other problem was just I need to get the data over to there, right? So, which once again, it's not that hard, but these things add up, and it's just like, why should we have to do them if something can exist that just takes care of it all for you? So that was a big part of it. And then the other problem with that system is it's just a key value store, so you couldn't do any kind of non-trivial manipulations of the data. So, and there was lots of other issues too, but that was the one that was the most database related. I think, we did store a lot of stuff in Oracle too. Orders of magnitude less, but every ad, every customer, every order, that kind of thing. Canned reports, like statistics on how many times was something served. And the statistics actually got to be a lot. Got to be like 100 million plus rows of statistics, right? Because you can slice and dice a little bit, and there's a lot of customers. And there was a little bit of pain there on performance. Another place there was some pain was on data processing, right? So, you have logs which, have 20 billion plus lines per day, and you want to crunch that, right? So that could be a lot. I mean, the logs could be, you can imagine logs being 20 terabytes, right, per day, and in the 1990s. So, and it's just how you do that in parallel, because you definitely needed multiple computers to do that. So, today there's sort of generalized abstractions for that, like MapReduce, right, which you may still need a good amount of hardware, but hopefully it'll scale linearly, and you can go to any scale you want. So that's a great thing, and it gives us this generalized framework that we can work with without having to build something out. And what we're now seeing, though, is that we're getting generalized frameworks for the database side of the same thing. It's like, how do I deal with a lot of data in a database where MapReduce is kind of how do I crunch a bunch of data.
So I got one for you. When dealing with lots of data, for example, relational database systems, right? Traditional master-slave replication style where you're dealing with a lot of writes, or you need to do analytics and what, you get to a point where you can only handle so much data because essentially you write to every box to have essentially the kind of data that, like to have it everywhere. And you run into limitations of how much can you vertically scale one machine. So it's kind of hard to scale that once you get to a certain point. When dealing with as much data as we have on the web, like, would you say that MongoDB is a lot more web scale than MySQL, for example?
Yes. I mean, I think you ask a good question or make a good observation about replication, because one way we can scale somewhat is to you know, have more servers that have a copy of the data, and you know, if I had one server with the data and I replicate it, now I have 5 servers with the data, I should be able to do 5 times as many queries per second, right? I can't do any more writes per second because every one of those 5 is going to do the write. So you can scale reads somewhat that way, but not writes. So if you're you know, very kind of read intensive, that's kind of a good pattern, at least historically. There are some nuances though. So imagine we did that, and we didn't do we didn't get fancy or anything, but I had one server, one MySQL server, whatever it is, and then I go to 5, right? They're doing replication, and I don't mind eventually consistent reads, right? So it's fine. And so I read from all 5 now, right? Well, one problem that will happen though is imagine each server had 100 gigabytes of RAM, right? The problem is they're all going to be caching the same data. They're all going to be caching the hottest data, right? The most recently touched data or most recently queried data, right? So they'll all work, but we didn't scale up the RAM in the system, right? I mean, we only have as much RAM as we had before, right? I.e., the system can cache 100 gigabytes of stuff, right? What we'd really like to do, though, is cache 500 gigabytes of stuff because we have 5 machines, and in aggregate, there's 500 gigabytes of RAM in them. So now you can solve that, right? You can say, okay, I'm going to intelligently send queries to different nodes of the 5 so that, you know, this one tends to cache this data from this 1/5 slice of the world, and this one. So you can do it, but it's just, you know, it starts, if you get rid of all the edges there, you start doing more and more and more work. So so I think the way to solve that is don't replicate, but partition, you know, shard, right?
Yeah, the only way I've seen that done in most relational implementations is by hand. So where certain table spaces are moved to different servers.
Yeah. There's a couple ways you can partition, right? One is functional, right? I'll put this systems table here, and this systems table is over here. Another way is by some key, right? Like by, author of the blog post or something. But you can do it, but you're going to do it yourself. I mean, we did that for one project at DoubleClick, you know, where we did manual sharding with MySQL. You know, it worked, but we had to do the work there. So, but coming back to that concept of sharding versus replication, I think our philosophy is, well, one, you're going to use both for different reasons, right? We think that sharding is the path to scaling, and that replication is important too, but not for that, but rather for kind of data safety and HA and disaster recovery, right? We need to have copies of the data on multiple machines just to get all those things, right? So we have replicas, but it's not to scale per se. So for example, if you have a cluster with 1,000 machines, one server will fail every day, right? So that's got to be seamless, right? We don't, the sysadmin developers, you know, they can't be hitting these things every day when something blips because it happens constantly, right? So, you know, if you have 1 or 2 machines, like 2 big Sun boxes, there aren't many failures per year of them, right? Because there are only 2 boxes, right? I mean, if one does fail, there's a lot of impact, but it doesn't happen often. So we can kind of manually deal with that, but with 1,000 or more, you can't. So the system needs to just handle that itself. And so we need some things like replication for that, and we also need kind of automatic failure and recovery for that. And there's different ways to kind of tackle that problem. One thing that's interesting is the way you approach it is quite different if you're doing strong consistency, right? Like the example before of where you had, I wanted to increment the votes and the voters at the same time, and only if this condition is true first. If you want that sort of capability out of the box, it actually changes the architecture a lot. Versus something like Amazon Dynamo can have a certain architecture, but that won't project very well out the strong consistency. I mean, Bigtable has strong consistency on a single row or whatever you want to call it, projection. So that's more of kind of the world that we're in.
Thank you.
Yeah, a couple other examples of where I think atomic operations are useful, and I think they come up pretty often. There's a big set of use cases where you don't even need them, right? Just a very simple thing, right? Say I have a website and I just want to register new users. And you pick your username, and it either says, thanks, you're registered, or it says, sorry, somebody's already got that username, pick a different one, right? So that's an atomic operation, right? We can't have a race condition where 2 people get the same username, right, at the same time. Another example is just a unique key constraint, right, on a piece of data. Like so in a relational database, a unique key constraint on a column. That requires atomic operations because it's you wouldn't want 2 things racing and then get 2 rows that have the same value, and they're not supposed to because of the unique constraint. And you can do that in Mongo. So that's kind of what pushed us in that direction. It's hard to see up here, so. Okay. All right, so thanks a lot. My email is dwight@tengen.com, and I think you guys know where to find us, and there's a lot of the community stuff on mongodb.org in terms of talking to people, too. Thanks a lot.